This is the second lecture on the gas laws packet, chapter 13. We're starting on the page that says Avogadro's principle. The particles that make up different gases are not the same size. Cl2 weighs 71, H2 weighs 2, so chlorine is by far much bigger than hydrogen. But Avogadro's principle states that equal volumes of gases at the same temperature and pressure will contain the same number of particles. So can a room be filled with basketballs, the same number of basketballs as the same number of marbles? And the answer is yes, if the particles have a lot of space between them. So if you think of the classroom, and if you put 20 basketballs in it, you could also put 20 marbles in it, because the container is much larger than the particles that they contain. Therefore, a collection of relatively large particles does not require more space than a collection of small particles. STP, standard temperature and pressure, from table A in the reference table, is 0 degrees Celsius and 1 atmosphere. If you have a mole of particles, of gas particles, 6.02 times 10 to the 23rd, they will occupy a volume of 22.4 liters no matter what the gas is. So here we have 3 tanks the same size, one with carbon dioxide, one with helium, and one with oxygen, but they each contain the same number of particles because they're at the same temperature and the same pressure. Real gases versus ideal gases. An ideal gas is a gas that obeys all of the laws of the kinetic theory. An ideal gas, though, is non-existent. There is no such thing as an ideal gas. An ideal gas obeys the gas laws, Boyle's law, Charles' law, Guy-Lussac's law, at all conditions of pressure and temperature. If this were true, the particles could have no volume, and they could not be attracted to each other. There is no gas for which this is true. All gases have volume, however small it might be, and all gas particles do have attraction for other gas particles, even if it's the very weak dispersion force in nonpolar molecules. An important behavior of real gases is that they can be liquefied and sometimes even solidified by cooling and applying pressure. Ideal gases cannot be. When will a gas be ideal? In other words, when is a gas a gas? When are the particles as far apart as possible? And that would be high temperature and low pressure. Low pressure means there's lots of space. When will a gas be non-ideal? When will a gas liquefy or condense or solidify? And the answer is at low temperature and high pressure. You have to know these two conditions. When is a gas ideal? When is a gas not ideal? You got to write this. The most ideal gas is the lightest gas. Which is hydrogen, H2. Then, the next lightest gas, the most closest to ideal, would be helium. The last part we have to cover is stoichiometry. Remember, that's balanced equations and ratios. So for volume, if STP is assumed, an equation can also relate volumes of gases. Remember, 1 mole of any gas at STP occupies 22.4 liters. So if you have 22.4 liters of N2 compare it in the equation, you will get 3 times as much H2, so 67.2 liters, and it will produce, compared to the N2, twice as much NH3, which is 44.8 liters. It's only that ratio thing. So if you have 10 liters of N2, 10 times what the equation shows, you will need 10 times as much hydrogen, or 30 liters, and twice as much ammonia will be produced, or 20 liters. So let's do a couple of quick questions and then we're done. So number 1, balance. And if you want to pause and balance these yourself and then turn this back on, that's up to you. I have a carbon and a carbon, that's okay. For number 1, 4 H's on the left, so I put a 2 in front. It gives me 2 plus 2, 4 oxygens, so I put a 2 in front of the O2. 1 is understood. For CH4 and CO2, so here's the question. If I have 22.4 liters of CH4, notice I circled it, how much O2 will be needed? So we can see we need twice as much according to the balanced equation, so 44.8 liters. Number 2, remember, pause if you want to balance it yourself. I have 6 carbons on the right, so a 6 in front. I have 12 H's on the right, so a 6 in front. I have on the left 12 plus 6, 18 oxygens. I have 6 here, so I need 12 more, so I put a 6 in front. It's comparing CO2 to O2. Well, we see it's a 1-to-1 ratio. So if I have 22.4 liters of CO2, I'm going to produce 22.4 liters of O2. Number 3, a calcium and a calcium, they balance, 2 H's. I have 4 H's on the right, so I put a 2 in front. It gives me 2 oxygens, which I have, so 1s are understood. So if I have 25.0 liters of calcium, officially I have to say if it's a gas, because the equation shows it's a solid. But if 25 liters of calcium react, how many liters of H2 will be produced? It's a 1-to-1 ratio, so 25.0 liters. Number 4, it's 3 carbons, put a 3 in front, 6 H's, put a 3 in front. This gives me 9 oxygens on the right, so I need 4.5 times 2 gives me 9. Since I'm only concerned about the ratio, I don't have to double everything. If I have 20 liters of this, then I need to make 3 times more, or 60 liters of CO2. Issue with the hydrogens, need a 2 in front and a 3 in front. 1 is understood. If 1 mole of N2 reacts, I'm going to make 2 moles of NH3, but it doesn't ask me for moles, it asks me for liters. 2 moles occupies 44.8. So that is the second lecture. If you have any questions about balancing or anything that we talked about here today, talk to me in class. You are not responsible for homework to do any of the questions in the textbook. If you want to, you can get a good start, but we're going to work on these in class. So I guess that's about it. I see we are gonna have a snow day on Tuesday, and hopefully you did this lecture here, and we'll see you Wednesday in class. Enjoy your day off.